So now before we run, we want to check a few things. First, let's just look at what we have in our model. We can see that we have the heated volumes that we created here for the BCs, and then that solid resistance plane to represent the thermal grease. And if we look at our solids, we have all of our components, the dielectric layer, that solid air layer at the bottom, at the base over the components, and then a heat sink and a PCB. So that all looks good. If we want to, we could do a member display just to have a look at what's going through, and looking in this we can see sort of everything that's at this layer. Lets you see what's overwriting what. You look either from the material or for the solids. That just lets you kind of easily visualize everything, make sure you don't have any gaps that you weren't intending to have, or have materials overwriting material, or have solids overwriting solids you weren't intending to do. Okay, so that all looks good. Now let's just quickly look at our parameters one last time here. We see we're in meters. That's what we were anticipating, the steady state and everything. Now looking at gravity, we're actually at -z. And that means that our gravity is coming down this way. When we look at our heat sink, that's not how we actually want to model it. We want to model it so that the heat sink is on top of the model. So for that case, we want to switch this to a Y positive. And keep, of course, the 9.8 still good. And hit apply on that. We're running it CFD. That's okay. And then looking at our solver here, by default, it's running with a flow of 0.1 convergence. Now, what that means is after the convergence criteria gets down to 0.1, it's going to stop the flow calculations, and it'll just update for temperature. In a lot of cases, that's all right. In this case, since it's so dominant on natural convection, I'm going to turn that off here, and we're just going to run it all the way down to the bottom here. Actually, maybe let's just turn it off just a little bit sooner, just to kind of make it go a little quicker at the end there. And that's something that through use you'll kind of get a good feel for it. But you can kind of watch how it's going. As long as it looks like your flow is developed when you're freezing it, that's fine. If your flow rate's still changing quite a bit, then that's going to give you inaccurate results. Okay, so with that set now, let's have a quick look at our mesh. Mesh looks okay, and we should be good to run. So we go to run and hit run here. Okay, that's going to bring up now our solver window, and we can see as it's running, there's several different screens. This will show any sensor temperature. We didn't actually put any sensors in, so that's just going to show the min and the max, and same there. And then this will show sort of what it's doing as it runs through, spitting out a lot of information from the solver. But our main screen here should give us what we're looking for. It tells us what position we're at, and then gives the temperature as it comes up. Okay, so I'm going to go ahead and pause this video. So it'll run. It shouldn't take too long here, maybe 10 minutes to run through the whole thing. So we can see that our model has converged here in about 35 iterations. And now we can come in and read the results. So our max temperature was 147. That's a little hot for these components. Really should only be probably around 125. As we look at this, we can look in various different planes here and sort of see how the flow's developed. If you want to look at the temperature at any given point, you can just click, and then if you wanted to change and look at, say, the velocity magnitude, we can see our max point is right in the middle of our model, which is what you would expect. So it looks like everything has converged nicely. Another feature that you can use is to actually update, if you want to look at temperature, we want to update it onto the actual original CAD geometry. You can do that. So if we go ahead and apply this will now go back to the CAD that we originally brought in and apply the temperature vectors on top of that. This edge length is just used to determine how small of the little triangular shapes it's going to put all over the CAD mesh to map it. So if we take a look at this, you can see now, for this it doesn't make much of a difference, but in some geometries it will actually make quite a bit of a difference. So it allows you to get a cleaner picture for any reports. Okay, so since that temperature was a little high, I think we'll try putting a fan on top of this now. Okay, so to put on a fan, we'll close off our results. And instead now we're going to go into BC and fan. Okay, and there's a few ways of dealing with a fan. You can have a rectangular or circular fan, and then you can either associate it to geometry or give it a specified region. For this case, we can just give a specified region here. Just we're not worried too much about the depth of it, and we want to put in a 120 millimeter fan. So if we pick a point close to the center of the model here, then